Show by the principle of mathematical induction that for all n belonging to the set of natural number, the following is true. Okay, let us begin. So here we begin by considering a statement denoted by P of n. So let P of n be the statement such that we have sine theta added to sine of 2 theta added to sine of 3 theta. So this is going to continue all the way up to the last term, which is given by sine of n theta. And the sum is going to be equals to sine of n plus 1 over 2 multiplied to theta times sine of n theta divided by 2 whole divided by, we have sine of theta over 2. Fine. Okay, so this is our statement. We're going to label this as statement number 1. So our goal will be to verify this statement. That's what we need to do by using the principle of mathematical induction. So we have to show that this statement is always true for any natural number that we pick up. Okay, so what we'll do first we are going to consider n to be equals to 1. So when we have n equals to 1, so we get P of 1, that's our statement. So P of 1 means we only have to consider the first term, or we can also take the nth term, which is sine n theta, replace n with 1. That's going to give us simply sine theta. So sine of theta, this is going to be equals to sine of, so we have n plus 1 over 2. So that's going to be 2 over 2 times theta multiplied to sine of n times theta over 2. So we have theta over 2 whole divided by sine of theta over 2. So when we simplify this, then the left hand side stays as sine theta. The right hand side, so we have sine 2 theta over sine theta, sine 2 over 2 theta. So that's simply sine theta. So we have sine theta multiplied to sine of theta over 2 whole divided by sine of theta over 2. We can factor out sine theta over 2 from the numerator and the denominator. So that's going to leave us with sine theta. So we have obtained that sine theta equals to sine theta. And this simply tells us that the statement P of 1 is true. So this is our statement P of 1. So P of 1 is true. Similarly, we can check out for n equals to 2, n equals to 3. However, we don't have to do that. We have to show that this statement is true for other natural numbers as well. So what we'll do here, we're going to assume that P of m is another statement, and we'll suppose that this is a true statement. So P of m is true. Now, what is P of m? So P of m is, we are going to take the help of the statement P of n, and then we're going to replace wherever we see n with m. So that means we have P of m such that we have sine theta added to sine 2 theta added to sine 3 theta. This goes all the way up to the last term, and the last term is simply the mth term. So that's given by sine of m theta, and this should be equals to sine of, so we had n plus 1 over 2, so we are going to replace that n with m, so that gives us m plus 1 over 2 times theta multiplied to sine of m theta divided by 2 whole divided by, so here we have sine of theta over 2. So let's call this statement number 2. So we're assuming that this is a true statement, and using this statement, our goal will be to show that the statement P of m plus 1 is true. To show, or we have to verify that P of m plus 1. Now, what is m plus 1 here? M plus 1 is the natural number that is consecutive to that of m. So we have to show that P of m plus 1, that is also true. Now, what does P of m plus 1 stand for? Now, P of m plus 1 is, this is simply the statement given by, we have sine theta added to sine 2 theta added to sine 3 theta. So this goes all the way up to, we have sine m theta. But since we are considering the consecutive term to m, so we will also have another term which is sine of m plus 1 of theta. Fine. And this is going to be equals to sine of, so here we'll have to replace this m with m plus 1. So that's going to give us m plus 2 divided by 2 of theta multiplied to sine of, so this m gets replaced with m plus 1. So we have m plus 1 times theta divided by 2 whole divided by sine theta over 2. So this is what we need to prove. Now how do we prove this? So we will be proving this by taking the help of statement number 2, because statement number 2 is a true statement. So let's call this statement number 3. So what we'll do, we're going to use statement number 1. So using statement number 2, statement number 3, so that is going to now become, we'll consider the left hand side only. We'll consider the left hand side of our expression. What is the left hand side? This entire expression. So let's note it down. So we have sine theta added to sine to theta going all the way up to sine m theta added to sine of m plus 1 theta. Now, luckily for us, we can consider the first term all the way up to the second last term, and we can replace with the right hand side of statement number 2. Okay, so that means we now have, sine of m plus 1 over 2 multiplied to theta multiplied to sine of m theta over 2 whole divided by, we have sine of theta over 2. This is going to get added to the second term, which is sine of m plus 1 over theta. However, what we'll do, we're going to apply a formula here. We're going to apply the half angle formula. So whenever we have sine of some angle theta, the half angle formula states that it can be also expressed as 2 times sine of half of the angle theta multiplied to cosine of half of the angle theta. So that means we now have 2 times sine of angle m plus 1 over 2 of times theta multiplied to cosine of the angle m plus 1 over 2 times theta. The reason why we applied the half angle formula here, because now we can take sine of m plus 1 over 2 times theta as a common factor from both of the two terms. So that means we have sine of m plus 1 over 2 times theta. So here we are taking this as the common factor, and also we're going to take the denominator as the common factor. So we have sine of theta over 2, which means our first term is now going to be left with sine of m theta over 2 added to 2 times cosine of angle m plus 1 over 2 times theta. Here we have taken sine of m plus 1 over 2 times theta as the common factor. But since we have also taken 1 over sine theta over 2 as the common factor, so we'll need to multiply it with sine of theta over 2. Fine. Okay, so let's go to the next step. Now here, we are going to combine, we're going to simplify this second term. So here, we're going to apply the formula. So whenever we have 2 times cosine of some angle A multiplied to sine of some angle B. So this is simply given by sine of the angle A plus B minus sine of the angle A minus B. So we're going to use this particular formula to expand the second term. That means we now have sine of m plus 1 over 2 times theta divided by sine of theta over 2. So this is going to get multiplied to sine of m theta over 2 added to. Now, so here we have sine of, so A corresponds to m plus 1 over 2 times theta and B corresponds to theta over 2. So let's write it down. So this angle, this is A, and theta over 2, so this is going to be B. So what is A added to B? So A when added to B, we're going to get m plus 2 over 2 multiplied to theta minus sine of angle m times theta over 2. Okay, so now we can cancel out the first term and the third term, and that is going to finally leave us with sine of angle m plus 1 over 2 times theta multiplied to sine of angle m plus 2 over 2 times theta whole divided by, we have sine of theta over 2. And this is exactly the expression on the right hand side. The expression on the right hand side. So let's check it out. Yes, so we have obtained exactly the right hand side of statement number 3. So this implies that we have successfully showed that the left hand side equals to the right hand side. And if that's the case, then we can say that our statement P of m plus 1, so this turns out to be a true statement as well. So that means we started out by considering P of m is true. So we started out with this condition that P of m is true, and this implies, that means we were able to show that P of m plus 1 is also true. This is also true. So now, by the principle of mathematical induction, we can generalize this and say that the statement P of n, this is going to be a true statement. And this is going to be true for all n belonging to the set of natural numbers. So hence, we have successfully verified a problem.